let's talk about the forces in chains, ropes, slings, springs. And it's important to talk about this right now at this stage of statics, right at the beginning, because in a statics course, you start the actual analysis of analyzing real systems, real life systems. You start with particle equilibrium. And in a lot of cases, particle equilibrium is associated with systems that have chains and slings and springs. That's why most of the example problems are going to have a chain or a sling. Okay, so these elements, these components, only support loads along their axis. So, in particular, chains and slings and ropes can't support compression, whereas where a spring can be in tension and compression, but you can't. There's no bending of the spring, twisting of the spring. Yeah, it can technically. I mean, you can pick up a spring with your hand and put bending load on it, but relative to we're talking. I mean, yeah, and even a chain, I guess you could kind of bend it, and the links would lock together, and you could it could technically support some kind of load when you bend it and twist the links together, technically. But when I'm saying that it can't support bending loads or twisting loads, I mean the way they're designed, like these chains relative to when you're talking relative to the loads that they're supporting in tension along their axis, the multi-ton loads they're supporting, what they can actually handle when they're twisted or bent is negligible. They can't support any kind of tonnage whenever you're bending it. You see, you could twist a sling, and I guess you could twist it and it'll resist being twisted by your hands, but compared to the tonnage of weight, if you applied an equivalent amount of tonnage of twisting to a sling like that, it would just tear apart. It would just tear, right? It would rip. Same thing like with a spring. It would you bent the spring. It's not designed for that. It would just bend, and it would fail because all of a sudden it would lose its dimension, and it would just fail. So springs, tension and compression along their axis, ropes, chains, slings, elements like that, only pulling forces, tension along their axis. Now that's another really, really important point, critically important point. Along their axis. Why is that so important? Because when you have a system with a chain, let's say, or I think this is a rope, well, the rope is going to be taut. It's holding a load. That's why you're analyzing the system. It's going to have a load under it. Well, because you know that the load has to be along the axis of the rope. You know the line of action of the rope force. So if you're analyzing for this system, you're going to do the free body diagram of this ring, let's say. You know, like this force here from rope BC, you know the line of action of it. You don't have to say this is some unknown angle theta. You know it. You're given the dimensions. It's 400 up 400. It's 45 degrees. Based on the geometry of the problem, you know its line of action. That's important. Same thing with a spring. You know this can support compression. Well, actually, if you look at this, for a spring can support compression, but in this scenario, the spring can't support compression because it's attached on each end to rope that can't support compression. So for this system, this spring can't support any compression. In general, a spring can support compression. But again, even for spring forces, you know the line of action of the force, right? This spring force is obviously to the left, but if the spring could be at an angle, and you're going to know the line of action of the spring force, so that's very important. That's very important to help you solve the problem you're dealing with. But springs can be even easier to work with than slings because you can determine the force in the spring. If you know the spring constant, and you will know the spring constant, you purchased the spring and it comes with a spring constant, then as long as you know the geometry of the problem and you know how much the spring is deflected, you know the force in the spring. You can't do that with slings. There's no you can't measure the deflection of a sling or a chain and directly tie that precisely to the force that's in the chain. Okay, and so then we talked about why these components are so closely associated with particle equilibrium problems. And so either in the previous video or we talk about this in the next video, particle equilibrium being the system you're analyzing or the component that the free body diagram of the component that you're analyzing, like a ring. All of the forces acting on it meet at a point. That point doesn't have to be the center of mass of the ring. So like, for example, if you have a ring that's kind of like this, and you've got a chain force here and a chain force here, and then coming from a crane, you have a force there. Well, we know the center of mass of the ring is here, but they meet at a point, the forces, but not at the center of mass. And so why that is, why it doesn't have to be the center of mass, that's a topic for another video. And we're talking about equilibrium. So the free body diagram of the component, it's not accelerating or most of the time not moving. Like it's not an unbalanced force it's not accelerating it, right? Particle equilibrium, the sum of the forces equal to zero. The sum of the forces on the component you're analyzing, they all meet at a point, and they all sum to zero. They're in equilibrium. Okay, and so really, typically in particle equilibrium problems, what you're seeing is you're going to have slings or chains all connected together by some component like a ring or some sort of connecting piece. And it's that connecting piece that is how you relate the two, one side of the system to another side of the system. But the characteristic is that, so what connects each rope to the connecting piece, it's not a rigid connection. Like it can move, like, so it's connected to the connecting piece with something like this, like a link. So it's not like it's welded to the connecting piece. So it can shift around into an equilibrium position to where the line of action of the chain on the connecting piece, or to where the line of action, it makes it so that the line of action of the force going into the connected piece is the exact same as the sling or the chain. If it was like welded there, then technically you could have the chain going straight up and down, but then actually this piece is transmitting like a bending load into the connector. But it's not like that. You see, it's like this. Like this piece can shift around on the ring to where everything's in line with the chain. So you've got this connecting piece, all of the forces acting on it are directly in line with the chain forces or the sling forces. So this is under all the forces acting on this central connector, or on the shackle, for example. This shackle here. These slings can move around to where the line of action of the force is all along the line of the slings. This piece here can shift around. It's not like welded to the pin. So this shackle is like a particle because all the forces acting on it are coming from those chain forces, and all those chain forces can't support any bending or twisting, right? It's all tension. So this shackle here, right? You'll have force here, and then as you pull the tension on it, all of the forces are going to shift around because the slings can move, and you'll end up getting this system where everything meets at a point. And so the free body diagram, this shackle is like a particle. So you can easily just sum the forces to equilibrium to find all of these sling forces. So that's kind of the general idea in these particle equilibrium problems. You're dealing with slings, ropes, and like pulleys, because even like with a pulley, the system can adjust itself, right? Like if you start and you put this in the middle, it's going to adjust itself. The pulley's going to roll down to an equilibrium position. Nothing is welded There's no like insane friction that's holding something from moving. It's all kind of governed by these tensile forces in the rope or the chain. And so the component that you do the free body diagram on, like this, I guess like this roller here, the roller can obviously support bending, or I mean you can, but all of the forces acting on it are coming from ropes and slings. Like this isn't a rope or a sling, but it's still indirectly just coming from a rope or a sling. So if you take kind of this frozen system right here to be the free body diagram, then all of the whole system's going to kind of find its equilibrium position because it's free to adjust to where all the forces meet at points. Like the main connecting element, the thing that's connecting the whole system together, it's going to be in particle equilibrium. They all meet at a point. And again, why this point is not like at the center of mass of the ring or of the wheel, that's a topic for another day, but they all meet at a point. And so all you're doing is you can just pretty much draw the problem as a point and just put all the forces acting at that point and run your equilibrium equations to solve for those forces. You'll know your angles because you know the line of action of the forces is going to be in the line along the line of the slings or the ropes.